252 million years ago, the planet entered a phase of climate stability unlike any before it, locking the world into a single, dominant condition: heat. Across Pangaea, a supercontinent spanning nearly all of Earth's landmass, average temperatures had climbed beyond 30 degrees Celsius in equatorial regions, with some interior zones approaching 40 degrees during peak seasons. This was not a passing fluctuation. Atmospheric carbon dioxide levels, already elevated from prior volcanic activity, continued to accumulate, reinforcing a thickening blanket of greenhouse gases. As heat absorption increased, evaporation outpaced precipitation across vast inland areas, and within a span of several 100,000 years, rainfall patterns that had sustained interior ecosystems began to fail. The result was a world losing its capacity to cool itself, an imbalance that would soon reshape every landscape it touched. By this stage, the interior of Pangaea had become a landscape defined by absence of consistent rainfall, absence of seasonal relief, and increasingly, absence of the rivers that had once sustained it. Evidence from sedimentary deposits across what is now South Africa, Russia, and parts of China indicates a dramatic shift in river systems during this period. Channels that had flowed continuously for millions of years began to narrow, braid, and in many cases, vanish entirely for extended stretches of the year. Current models suggest that average annual precipitation in these regions dropped by as much as 50% over a span of roughly 1 million years, a rapid shift by geological standards, though imperceptible within a single lifetime. As river flow diminished, the wetlands that depended on consistent water input began to contract. Floodplains that had once supported dense vegetation and standing water for most of the year now held moisture for only a few weeks following seasonal rains. Soil moisture levels, critical for root systems and microbial activity, fell below thresholds required to sustain mature forest cover in many lowland areas. The consequence was a measurable reduction in vegetation density, with some fossil soil horizons, paleosols, showing root traces that become progressively shallower and more sparse through successive rock layers, spanning several 100,000 years of deposition. This decline in vegetation initiated a feedback process that would intensify the drying trend already underway. Plant cover plays a direct role in regulating surface temperature and moisture retention. Root systems stabilize soil, while leaf canopies reduce direct solar exposure to the ground and slow evaporation rates. As plant cover thinned, exposed soil absorbed and radiated more heat, raising local surface temperatures by several degrees Celsius compared to vegetated zones nearby. This additional heat further accelerated evaporation from any remaining surface water, compounding the water deficit. Within affected regions, this cycle reduced vegetation leading to increased heat leading to further vegetation loss, repeated and reinforced itself across multiple cycles of wet and dry seasons. The animals occupying these environments had evolved under conditions very different from those now developing. Temnospondyls, a group of large amphibians that had dominated freshwater ecosystems for tens of millions of years, depended on permanent bodies of water for reproduction, thermoregulation, and basic hydration. Species such as those belonging to the genus Lydecarina, found in deposits across the Karoo Basin, required water depths sufficient to submerge bodies, often exceeding 1 meter in length. As pools and channels began drying for extended periods, sometimes lasting several months longer than in previous geological intervals, populations of these amphibians became increasingly concentrated into smaller, isolated bodies of water. This concentration carried direct physiological consequences. Reduced water volume meant less dissolved oxygen available to support aquatic respiration, a critical factor for amphibians that rely partly on gill or skin-based gas exchange during portions of their life cycle. Laboratory studies of modern amphibian physiology indicate that oxygen depletion in shallow, warm water can occur rapidly, within hours, once water temperatures exceed approximately 25 degrees Celsius. a threshold increasingly common in shrinking Permian pools exposed to direct sunlight for most of the day. Evidence from fossil assemblages shows mass mortality layers, in which numerous individuals of the same species are preserved together, consistent with die-off events linked to deteriorating pool conditions during prolonged dry intervals. For larger reptiles inhabiting these same landscapes, the challenges were different but equally direct. Many synapsid groups, an evolutionary lineage that includes the ancestors of mammals, had body sizes ranging from under a meter to over 3 meters in length, with correspondingly high metabolic demands. As ambient temperatures rose, these animals faced increasing difficulty in regulating internal body temperature through behavioral means alone. Burrowing, a strategy used by smaller species to escape surface heat, became less effective as soil itself absorbed and retained heat to greater depths, with some estimates indicating that subsurface temperatures at half a meter depth increased by 3 to 5 degrees Celsius compared to earlier in the same geological interval. The cracking of exposed ground became a visible record of these changes. As soil moisture dropped below levels needed to maintain cohesion, clay-rich sediments contracted, forming networks of desiccation cracks that, in some preserved surfaces, extend to depths of 20 to 30 centimeters and span widths of several centimeters at the surface. These cracked surfaces, preserved in rock layers across multiple sedimentary basins, indicate repeated cycles of wetting and drying, with each cycle leaving the ground slightly drier than before. Over a span estimated at several 100,000 years, these cycles compounded, transforming what had been continuous floodplain environments into fragmented landscapes of isolated, shrinking water bodies separated by increasingly large stretches of cracked, exposed ground. Above these landscapes, the atmosphere itself was changing in ways that reinforced surface conditions. With reduced vegetation cover, less moisture was being returned to the air through transpiration, the process by which plants release water vapor through their leaves. This reduction in atmospheric moisture meant fewer clouds formed locally, resulting in less shade and more direct solar radiation reaching the surface during daylight hours. Estimates based on comparable modern arid transitions suggest that cloud cover in affected regions may have decreased by 20 to 30% over the course of this drying interval, allowing surface temperatures to climb several degrees higher during peak daylight hours than they would have under earlier, more humid conditions. By the close of this phase, the landscape bore little resemblance to the lush floodplain ecosystems that had existed only a few 100,000 years earlier. Rivers that had once flowed year-round now ran only during brief seasonal pulses, if at all. Wetlands that had supported diverse communities of amphibians and early reptiles had contracted into scattered remnants, each one a temporary refuge, increasingly unable to sustain the populations depending on it. The cracked, sun-baked ground, extending across these former floodplains, stood as physical evidence of a climate system that had crossed a threshold, one in which the mechanisms that had once moderated temperature and moisture had ceased to function, leaving the landscape with no internal capacity to cool or recover. As the floodplains of the late Permian continued to fragment, the remaining bodies of water became focal points for the largest predators of the period. Among these, Gorgonopsians, a group of carnivorous synapsids, occupied a dominant position within terrestrial food webs. Species such as Innostrancevia, known primarily from deposits in the Russian Vyatka region, reached body lengths of up to 3.5 meters, with skulls measuring over 40 centimeters and canine teeth exceeding 12 centimeters in length, including the root. These proportions indicate an animal adapted to subdue prey substantially large in body mass, likely through a combination of ambush positioning and a powerful, slashing bite. The behavioral ecology of Gorgonopsians during this period was shaped directly by the changing distribution of water and prey. As permanent water sources became scarce, herbivorous species, including dicynodonts, a group of tusked, barrel-bodied synapsids that formed the primary prey base in many ecosystems, were forced to concentrate around the remaining wetland margins for extended periods, particularly during dry seasons that, by this stage, could last several months longer than in earlier geological intervals. This concentration of prey around predictable locations created conditions favorable for predators relying on ambush strategies, since cover near shrinking water margins, reeds, low vegetation, and exposed riverbank sediment provided opportunities for concealment within a few meters of approach distance. Fossil trackways preserved in fine-grained mudstone from this period, found in multiple basins across what is now South Africa and Russia, show patterns consistent with this dynamic. In several documented sequences, dicynodont tracks approaching a water margin are followed within the same sedimentary layer by Gorgonopsian tracks intersecting the same path at an oblique angle, evidence interpreted as consistent with pursuit behavior occurring over distances of less than 10 meters. The proximity of these trackways to preserved drag marks and, in at least one case, a partial dicynodont skeleton bearing puncture marks spaced approximately 8 centimeters apart, consistent with Gorgonopsian canine spacing, provides direct physical evidence of predation events tied to these constrained water margin environments. At the same time, the amphibians occupying these waterways faced their own set of pressures, while simultaneously representing a secondary threat to smaller animals sharing the same habitat. Temnospondyle amphibians of this period, including large-bodied forms reaching lengths of over 2 meters, retained a body plan adapted for life in open water, flattened skulls, laterally positioned eyes, and powerful tail musculature suited for ambush from a submerged position. As water bodies shrank in surface area but, in many cases, increased in relative depth near their centers due to continued sediment accumulation along the margins, these amphibians became increasingly concentrated within smaller volumes of water, alongside the very prey species, smaller reptiles, fish, and juvenile synapsids, on which they depended. This concentration intensified predation pressure within the water itself. Stomach contents preserved in several temnospondyle specimens from this interval include partially digested remains of smaller tetrapods, indicating that as alternative food sources became scarcer on land, aquatic predators increasingly relied on prey items drawn to the water's edge by the same scarcity affecting the broader landscape. In effect, the shrinking wetlands functioned as a converging point for multiple trophic levels simultaneously. Herbivores seeking water, terrestrial predators seeking herbivores, and aquatic predators seeking any animal entering or approaching the water margin. The physical conditions within these remaining water bodies placed direct constraints on the animals occupying them. Water temperatures in shallow pools exposed to direct sunlight for most of the day could reach 28 to 32 degrees Celsius during peak hours. Based on comparisons with similar modern shallow water systems in tropical and subtropical regions, at these temperatures, dissolved oxygen levels decline significantly, often falling below concentrations required to support large-bodied aquatic animals for extended periods. For temnospondyles relying partly on cutaneous, skin-based gas exchange, this meant increasing physiological stress during the warmest portions of the day, likely restricting active hunting behavior to early morning and dusk periods when water temperatures were comparatively lower. For Gorgonopsians and other terrestrial predators, the increasing scarcity of prey introduced a different set of pressures. As dicynodont populations declined in response to vegetation loss, since these herbivores depended on the same plant communities that were thinning across the landscape, predator populations faced a corresponding reduction in available biomass. Evidence from relative abundance patterns in fossil assemblages from this interval indicates a measurable decline in dicynodont specimens relative to predator specimens over a span of several 100,000 years, a ratio shift that, under modern ecological models, would be associated with increased competition among predators and, in some cases, increased reliance on smaller or less typical prey items. This shift towards smaller prey is reflected in changes to tooth wear patterns observed in some Gorgonopsian specimens from the later portion of this interval. Microscopic analysis of enamel surfaces shows an increase in the frequency of fine scratches and pitting consistent with contact with bone, a pattern that becomes more pronounced in specimens recovered from higher, and therefore later, stratigraphic levels. This is consistent with increased consumption of smaller-bodied prey, where bone-to-tooth contact during feeding would occur more frequently than when processing the larger, more substantial carcasses of fully grown dicynodonts. The cumulative effect of these pressures was a landscape in which predator-prey dynamics had become increasingly compressed, both spatially and temporally. Where earlier ecosystems had distributed predation events across a broad mosaic of habitats, river channels, floodplain margins, upland areas, and scattered pools, the drying trend had reduced viable habitat to a series of isolated, shrinking refuges. Within these refuges, the spatial separation that had once existed between different predator types and between predators and prey diminished considerably. Animals that under earlier conditions might rarely have encountered one another were now sharing the same narrow margins of mud and water for extended portions of each day. By the end of this interval, the remaining wetlands of the late Permian had become environments defined by concentration and constraint, concentration of multiple species into shrinking habitable space, and constraint imposed by rising temperatures, declining oxygen levels, and a steadily narrowing base of available prey. The predators that had once occupied a landscape offering abundant space and resources now operated within a system where every remaining water source represented both a necessity and a point of convergence, drawing together herbivores, amphibians, and apex predators into the same diminishing margins, under conditions that left increasingly little room for avoidance or retreat. While wetland environments fragmented under the pressures of declining rainfall, the forested regions of Pangaea, particularly those at higher latitudes, where conditions had remained comparatively temperate, faced a related but distinct set of changes. These forests, dominated by conifer-like gymnosperms such as Glossopteris in the southern continents and various Corditalian groups in equatorial and northern regions, had formed extensive, continuous canopy systems covering areas spanning hundreds of thousands of square kilometers. Tree heights in these forests commonly reached 15 to 20 meters, with some specimens of preserved trunk material indicating diameters exceeding 1 meter, suggesting individual trees with lifespans extending across multiple centuries. The stability of these forest systems had, for tens of millions of years, depended on a relatively narrow range of climatic conditions. Consistent seasonal rainfall, moderate temperature ranges typically between 10 and 25 degrees Celsius, and atmospheric carbon dioxide concentrations that, while elevated compared to more recent geological periods, remained within bounds that supported sustained photosynthetic activity without inducing significant physiological stress. As atmospheric carbon dioxide levels continued to rise during this interval, estimates based on stomatal density in preserved leaf fossils suggest concentrations increasing from approximately 1,000 parts per million to over 2,500 parts per million across a span of roughly 500,000 years. This balance began to shift. Elevated carbon dioxide levels initially produced a measurable physiological response in surviving plant tissue. Stomata, The small pores on leaf surfaces that regulate gas exchange and water loss decreased in density by as much as 30 to 40% in some preserved leaf specimens from this interval compared to specimens from earlier deposits. This reduction represents a plant-level adaptation to higher carbon dioxide availability, allowing for reduced water loss per unit of carbon dioxide absorbed. However, this adaptation carried a secondary consequence. Reduced stomatal density also limits a plant's capacity for transpirational cooling, the process by which water evaporation from leaf surfaces reduces leaf and surrounding air temperature. With this cooling mechanism diminished across large forested areas, localized temperatures within forest canopies began to rise, with estimates suggesting increases of 2 to 4 degrees Celsius above baseline conditions recorded in earlier deposits from the same regions. This temperature increase, while modest in isolation, interacted with declining precipitation patterns already affecting lower latitude regions and gradually extending poleward. Soil moisture data inferred from paleosol analysis indicates that, over a span of approximately 300,000 years, available water in forest soils during dry seasons decreased by an estimated 25 to 35% in several sampled regions. For mature trees with root systems extending 2 to 4 meters in depth, this reduction initially had limited visible effect, as deeper root networks could access residual moisture unavailable to smaller plants and ground-level vegetation. However, the understory layer, ferns, smaller seed plants, and ground cover that formed the base of the forest food web showed more immediate signs of stress, with fossil leaf litter from this interval showing increased frequency of curled, desiccated leaf margins, consistent with water stress responses observed in modern plants under drought conditions. The animals occupying these forest ecosystems depended on this multi-layered structure for both shelter and food resources. Insect diversity during this period was substantial, with preserved specimens indicating the presence of large dragonfly relatives with wingspans exceeding 40 centimeters, alongside diverse populations of beetles, cockroach relatives, and early hemipteran insects. Many of these species depended on specific plant hosts for both larval development and adult feeding, creating tightly linked relationships between insect populations and particular components of the forest's plant community. As understory vegetation began to decline in density and diversity, insect populations dependent on these specific plants showed corresponding reductions, evidenced by decreasing diversity in preserved insect wing fossils from successive stratigraphic layers within the same localities. Small reptiles inhabiting forest floor and leaf litter environments, including early diapsids and procolophanid-related forms, typically under 50 centimeters in length, relied on this insect abundance as a primary food source. These animals occupied a microhabitat characterized by relatively stable humidity and temperature, buffered by the canopy above and the moisture-retaining leaf litter below. As canopy cooling diminished and understory vegetation thinned, this buffering effect weakened. Temperature fluctuations at ground level, previously moderated to a range of perhaps 5 to 8 degrees Celsius between day and night, began to widen, with some modeled estimates suggesting daily temperature ranges increasing to 12 to 15 degrees Celsius in affected areas, a shift that would have required increased behavioral thermoregulation from ectothermic animals previously adapted to more stable conditions. The forest dieback that began to manifest during this interval did not occur uniformly or instantaneously across the landscape. Instead, evidence from multiple sedimentary sequences indicates a pattern of progressive canopy thinning, beginning at the margins of forested regions, areas already closer to the climatic thresholds separating forest from more open woodland or savanna-like vegetation, and gradually extending toward what had previously been climatically stable forest interiors. pollen and spore assemblages from this interval show a measurable shift in composition, with the relative abundance of conifer and cordytalian pollen decreasing by as much as 40 to 50% in some sequences, while spores from drought-tolerant fern species show a corresponding increase, indicating a shift in dominant vegetation type even where complete forest loss had not yet occurred. This shift in vegetation composition had direct consequences for the broader carbon cycle operating within these ecosystems. Mature forest systems of this scale had functioned as substantial carbon reservoirs, with photosynthetic activity offsetting a portion of the carbon dioxide being released into the atmosphere through ongoing volcanic activity in other regions. As forest cover declined and canopy photosynthetic capacity diminished, this offsetting effect weakened correspondingly. Current models estimate that the carbon sequestration capacity of these forest systems may have declined by 20 to 30% over the course of this dieback interval, removing a mechanism that had previously moderated, to some degree, the rate of atmospheric carbon dioxide accumulation. By the close of this interval, large sections of what had been continuous forest cover showed visible signs of transition. Canopy density reduced in many areas, from near-complete coverage to coverage estimated at 50 to 60% of previous levels, based on comparative analysis of fossil leaf accumulation rates in lake and floodplain deposits adjacent to forested zones. The animals and insects that had depended on the specific conditions provided by dense, continuous canopy, stable humidity, moderated temperature, and a diverse understory food web faced an environment increasingly different from the one their populations had occupied for the preceding several million years. The forests themselves remained present across the landscape, but their internal structure, productivity, and capacity to support the food webs that had developed within them had begun a measurable and, evidence suggests, continuing decline. As forest dieback progressed and wetland habitats continued to fragment, the apex predators occupying these landscapes encountered conditions increasingly distinct from those their populations had experienced over previous evolutionary timescales. Gorgonopsians and other large carnivorous synapsids had developed within ecosystems characterized by relatively predictable prey distribution, where herbivore populations moved across extensive ranges in response to seasonal vegetation patterns spanning tens of thousands of square kilometers. As vegetation cover declined and water sources became increasingly localized, the ranging patterns of herbivorous prey species shifted correspondingly, concentrating into smaller geographic areas for longer portions of each year. This concentration of prey produced a corresponding concentration of predator activity. Evidence from fossil site density, the number of predator specimens recovered per unit area of exposed sedimentary rock, shows an increase in several basins dating to this interval, with some localities yielding Gorgonopsian remains at densities 2 to 3 times higher than in equivalent rock units from several 100,000 years earlier. This pattern is consistent with multiple individual predators occupying overlapping territories within areas that, under earlier conditions, might have supported only a single resident predator population. Territorial overlap among large predators carries direct behavioral consequences, based on comparative studies of modern large carnivores occupying similarly constrained habitats. Reduced spatial separation between individuals increases the frequency of direct encounters, which in turn increases the likelihood of conflict over access to prey, water, or shelter. Skeletal evidence from several Gorgonopsian specimens recovered from this interval shows healed fractures and puncture wounds in regions of the skull and limb girdle consistent with bite marks from animals of similar size and dental. Morphology patterns interpreted as evidence of intraspecific conflict, meaning conflict between individuals of the same or closely related species, rather than predator-prey interactions. The frequency of such injuries appears to increase in specimens recovered from progressively higher, and therefore later, stratigraphic levels within the same sedimentary sequences. In one documented sample set from the Karoo Basin, the proportion of Gorgonopsian specimens showing healed cranial trauma increases from approximately 8% in lower stratigraphic units to over 20% in units, deposited an estimated 200,000 to 300,000 years later. While sample sizes for such analyses remain limited, and caution is warranted in drawing firm conclusions from relatively small datasets, this pattern is consistent with increased competitive interaction among predators occupying habitats with declining resource availability. As preferred prey species, particularly larger dicynodonts, declined in both population size and average body mass, predators faced a corresponding shift in the energetic returns available from successful hunting. A single large dicynodont, with body mass potentially exceeding 100 kilograms in earlier populations, could provide sufficient nutrition to sustain a Gorgonopsian for an extended period, potentially a week or more, based on metabolic rate estimates for animals of comparable size. As average dicynodont body mass decreased, evidenced by a measurable reduction in limb bone diameter and overall skeletal proportions in specimens from later stratigraphic levels, suggesting average mass reductions of perhaps 20 to 30%, predators required more frequent successful hunts to meet equivalent energetic needs, increasing both hunting frequency and the associated risks of injury or failed pursuit. Under these conditions, scavenging behavior likely became an increasingly significant component of predator feeding strategies, supplementing direct predation. While scavenging is difficult to document directly in the fossil record, indirect evidence comes from tooth marks preserved on bones that show no evidence of having been part of a fresh kill, specifically bones exhibiting weathering patterns consistent with surface exposure for periods of weeks to months prior to the application of tooth marks. Several specimens from this interval show exactly this combination: weathering consistent with prolonged surface exposure, followed by tooth marks consistent with Gorgonopsian dental morphology, suggesting that carcasses of animals that had died from causes other than direct predation, potentially including starvation or heat stress related to the broader environmental decline, were subsequently utilized as food. Sources: the energetic cost of locating increasingly scattered and unpredictable food sources placed additional physiological demands on large predators already operating near the upper limits of body size, sustainable under declining environmental conditions. Larger body size generally correlates with higher absolute metabolic requirements, meaning that the largest individuals within predator populations would have faced proportionally greater difficulty meeting energetic needs as prey availability declined. This dynamic is consistent with evidence from body size distributions in predator populations from this interval, which show a measurable decrease in maximum body size over time, even as minimum body sizes within the same populations remain comparatively stable, a pattern suggesting that the largest individuals face disproportionate survival challenges under these changing conditions. For smaller predatory species, including various therocephalian groups, a separate lineage of carnivorous synapsids, typically ranging from 30 centimeters to just over 1 meter in body length. The dynamics of this period presented a somewhat different set of challenges and, in some cases, opportunities. Smaller body size correlates with lower absolute energetic requirements and, in many cases, greater dietary flexibility, including the ability to subsist on smaller prey items such as insects, small reptiles, and juvenile animals of various species. Fossil evidence indicates that several smaller therocephalian species maintained relatively stable population densities through this interval, even as larger predator populations showed measurable decline, consistent with the principle that smaller-bodied generalist predators often demonstrate greater resilience under conditions of declining resource availability. This divergence in outcomes between larger and smaller predator species represents an early indication of a broader pattern that would become increasingly pronounced as environmental conditions continued to deteriorate. A gradual shift in the relative success of different body size classes, favoring smaller, more dietarily flexible animals over larger, more specialized ones. The largest predators of the late Permian animals that had occupied dominant positions within their ecosystems for millions of years, supported by abundant large prey and extensive territorial ranges, now operated within landscapes where the very characteristics that had contributed to their success, namely large body size and dietary specialization toward large prey, had become increasingly disadvantageous. The hunters that had once defined the upper limits of the food chain within these ecosystems now faced a set of pressures for which their evolutionary history had provided no direct precedent. While terrestrial ecosystems across Pangaea continued to fragment under the combined pressures of rising temperature and declining precipitation, marine environments surrounding the supercontinent's coastlines were undergoing a parallel set of changes, driven by related but distinct mechanisms. Late Permian oceans had, for tens of millions of years, supported extensive reef systems built primarily by calcifying organisms, including various sponge groups, bryozoans, and calcareous algae, forming structures that in some regions extended for hundreds of kilometers along continental shelf margins, with individual reef complexes reaching thicknesses of several hundred meters, accumulated over millions of years of growth. These reef systems depended on a relatively narrow range of conditions for sustained growth: water temperatures typically between 20 and 28 degrees Celsius, stable salinity levels, and consistent availability of dissolved oxygen and nutrients delivered through ocean circulation patterns. As global temperatures continued to rise during this interval, a trend driven by the same atmospheric carbon dioxide accumulation affecting terrestrial climate systems, surface ocean temperatures in many regions began to exceed this upper threshold. Isotopic analysis of preserved shell material from this interval indicates surface water temperature increases of approximately 3 to 5 degrees Celsius over a span of roughly 400,000 years in several sampled locations, pushing conditions in some shallow reef environments to 30 degrees Celsius or higher during warmer seasonal periods. Elevated water temperature affects marine calcifying organisms through multiple interacting mechanisms. Increased temperature reduces the solubility of dissolved oxygen in seawater, meaning that warmer water holds less available oxygen for respiration, even when atmospheric oxygen levels remain constant. Additionally, increased temperature raises the metabolic rate of most marine organisms, increasing their oxygen demand at precisely the point when oxygen availability is declining. For reef-building organisms, which often exist as dense colonial structures with limited capacity for individual movement to more favorable conditions, this combination of increased demand and decreased supply created sustained physiological stress over extended periods. Evidence of this stress is preserved in the growth structure of calcified skeletal material from this interval. Cross-sections of preserved reef-building organisms show growth band irregularities, zones of reduced density, and irregular spacing that become increasingly frequent in samples from progressively later stratigraphic levels. These irregularities are consistent with periods of growth interruption, during which the organism's normal calcification processes were disrupted, likely in response to temperature or oxygen-related stress exceeding the organism's tolerance range. In some sampled reef sections, The frequency of these growth interruptions increases from less than 5% of examined growth bands in lower stratigraphic units to over 25% in units deposited approximately 300,000 years later. The decline of reef-building organisms had direct consequences for the broader marine communities that depended on reef structures for habitat. Reef systems of this period supported diverse assemblages of associated organisms, including various mollusk groups, echinoderms, and numerous arthropod species that utilized the complex three-dimensional structure of reefs for shelter, feeding, and reproduction. As reef growth slowed and, in some areas, reversed, with evidence of net erosion exceeding new growth in several sampled sections, the habitat complexity available to these associated organisms declined correspondingly, measured through a reduction in the diversity of preserved shell and skeletal material within reef-associated sediment layers. Trilobites, a group of marine arthropods that had been present in oceanic ecosystems for over 270 million years by this point, represent one of the more thoroughly documented groups showing decline during this interval. Trilobite diversity, measured as the number of distinct species identified within sampled stratigraphic intervals, shows a measurable reduction across multiple ocean basins during this period, with some sequences showing a decrease from 15 to 20 identifiable species in lower units to fewer than 8 species in units deposited several 100,000 years later. While trilobites as a group had already experienced significant diversity declines over the preceding tens of millions of years for reasons unrelated to this specific interval, the rate of decline during this period appears, based on current stratigraphic dating, to exceed background rates observed in earlier portions of the group's evolutionary history. Brachiopods, a group of shelled marine invertebrates that had been among the most abundant and diverse components of Paleozoic marine ecosystems, show a similar pattern of decline during this interval, though the underlying mechanisms appear somewhat distinct from those affecting trilobites. Brachiopod shells are composed primarily of calcium carbonate, and their formation depends on the availability of carbonate ions in seawater availability that is directly affected by water temperature and, to a lesser degree during this specific interval, by changes in ocean water chemistry that were beginning to develop as a consequence of increased carbon dioxide absorption by ocean water from the atmosphere above. Larger marine predators, including various cephalopod groups, with shell diameters reaching up to 30 centimeters, and several lineages of marine reptiles that had begun to diversify during the preceding tens of millions of years, depended on the productivity of these reef-associated and broader marine food webs for sustenance. As the diversity and abundance of smaller invertebrates declined, these predators faced a corresponding reduction in available prey. Though the effects on predator populations during this specific interval appear, based on currently available fossil evidence, to lag somewhat behind the more immediate declines observed in reef-building organisms and their directly associated invertebrate communities, a pattern consistent with the generally slower population response times typically observed in larger-bodied organisms occupying higher positions within food web structures. By the close of this interval, marine environments that had, for tens of millions of years, supported some of the most diverse and structurally complex ecosystems on the planet showed clear evidence of transition. Reef structures that had previously functioned as centers of biological productivity and habitat complexity now showed reduced growth rates, increased erosion, and declining associated biodiversity. The mechanisms driving these changes, rising water temperature, declining dissolved oxygen availability, and shifting ocean chemistry, were each individually measurable, yet each was also beginning to interact with and reinforce the others, establishing conditions that would continue to develop in the intervals that followed. As reef ecosystems continued their measurable decline, a more extensive transformation was developing within the deeper and more widespread regions of the global ocean, driven by a mechanism distinct from, though related to, the localized temperature stress affecting shallow reef environments. This mechanism centered on the availability of dissolved oxygen throughout the water column, a factor that, under stable conditions, is maintained through a combination of atmospheric exchange at the ocean surface and the circulation of oxygen-rich surface water into deeper layers through processes including wind-driven mixing and density-driven downwelling in polar regions. As global surface temperatures continued to rise during this interval, the temperature difference between surface and deep ocean water decreased. Under typical conditions, colder, denser water at the poles sinks and flows toward the equator at depth, carrying dissolved oxygen into deeper ocean layers in a circulation pattern that can take centuries to complete a full cycle. As polar regions warmed, the density difference driving this circulation diminished, and current models indicate that the rate of this deep water formation and circulation slowed measurably during this interval, with some estimates suggesting reductions in deep water renewal rates of 30 to 50% compared to baseline conditions established in earlier portions of the Permian. The consequence of this slowing circulation was a progressive reduction in the resupply of oxygen to deeper ocean layers, even as oxygen consumption within these layers continued at rates determined by the metabolic activity of organisms living within them, as well as by the decomposition of organic material sinking from more productive surface waters above. Without adequate resupply, dissolved oxygen concentrations in affected deep water regions began to decline steadily, a process that, based on the rates indicated by geochemical proxies preserved in sedimentary rock from this interval, may have unfolded over a span of several 100,000 years across large areas of ocean basin. Geochemical evidence for this oxygen decline comes primarily from the analysis of specific elements and isotopes preserved within marine sediments, which behave differently depending on whether they were deposited under oxygen-rich or oxygen-poor conditions. Sediments from this interval show increasing concentrations of elements such as molybdenum and uranium relative to typical crustal abundances, a pattern that occurs specifically under low oxygen conditions, as these elements become more soluble and are preferentially incorporated into sediment under such circumstances. The degree of enrichment observed in sediments from this interval in some sampled locations increases progressively through successive stratigraphic layers, indicating an expansion of low oxygen conditions over time rather than a sudden onset. As oxygen concentrations in affected deep water regions declined below approximately 2 mg per liter, a threshold below which most complex marine animals, including fish, mollusks, and arthropods, experience significant physiological stress and, below roughly 0.5 mg per liter, cannot survive for extended periods. These regions became progressively less habitable for the majority of marine animal life that had previously occupied them. The spatial extent of these low oxygen zones is estimated, based on the geographic distribution of sediment samples, showing the relevant geochemical signatures to have expanded considerably during this interval, potentially affecting areas of ocean floor measuring in the millions of square kilometers by the latter portion of this period. The expansion of low oxygen water was not confined solely to deep ocean regions. In several documented sequences, evidence indicates that low oxygen conditions extended into shallower continental shelf environments as well, areas that under earlier conditions had maintained well-oxygenated water due to their proximity to the surface and exposure to wind-driven mixing. The upward and shoreward expansion of low-oxygen water into these shallower zones is consistent with a process sometimes referred to as the shoaling of the oxygen minimum zone. The boundary between oxygen-rich surface water and oxygen-poor deeper water, moving closer to the surface as the overall volume of oxygenated water in the ocean decreased. For animals inhabiting continental shelf environments, this upward expansion of low oxygen water represented a direct and, in many cases, sudden encroachment into habitats that had previously been entirely suitable for their physiological requirements. Unlike the gradual habitat contraction affecting terrestrial wetland environments during this same broad interval, the expansion of low-oxygen water into shelf environments could, based on the rates suggested by some sedimentary sequences showing rapid transitions in geochemical indicators across relatively thin rock intervals, occur over periods as short as several thousand years in specific locations, rapid by geological standards, though still gradual relative to the lifespan of individual organisms. Beyond simple oxygen depletion, geochemical evidence from several sedimentary sequences indicates the presence of hydrogen sulfide within affected water masses. During this interval, a compound that forms under conditions of complete oxygen absence through the metabolic activity of certain bacteria that utilize sulfate rather than oxygen for respiration. Hydrogen sulfide is directly toxic to most animal life, even at relatively low concentrations, with toxicity occurring through interference with cellular respiration processes that are largely conserved across diverse animal groups. The presence of biomarkers associated with sulfate-reducing bacteria in sediments from this interval, identified through analysis of preserved organic molecules, indicates that hydrogen sulfide production was occurring within affected water masses, and in some cases may have extended into the photic zone, the depth range, receiving sufficient light for photosynthesis based on the presence of biomarkers associated with bacteria that require both light and hydrogen sulfide for their specific metabolic processes. Within this expanding zone of low oxygen and, in places, sulfide-bearing water, the organisms able to persist were necessarily limited to those possessing specific physiological adaptations for tolerating such conditions. Certain bacterial groups, as indicated by the biomarker evidence described above, were capable of thriving under exactly these circumstances, in some cases reaching population densities sufficient to produce visible effects on sediment, color, and composition, with some sedimentary layers from this interval showing distinctive lamination patterns interpreted as resulting from dense microbial mat development on the seafloor structures that, under more oxygenated conditions, would typically have been disrupted by the burrowing and feeding activity of larger animals, activity that the geochemical and fossil evidence indicates had become substantially reduced or absent in these affected areas by this point in the interval. While oceanic and atmospheric systems continued to develop the conditions described in the preceding interval, a separate and geographically distinct process was underway in the region of Pangaea that corresponds, in present-day geography, to central Siberia. This process involved the eruption of vast volumes of basaltic lava from a series of volcanic vents distributed across an area that, based on the current extent of preserved volcanic rock and associated intrusive deposits, covered approximately 2 to 3 million square kilometers, an area comparable in scale to a substantial portion of a modern continent. The volcanic activity in this region, now referred to by geologists as the Siberian Traps, was not the product of a single eruption or even a series of discrete eruptive events in the conventional sense. Instead, current dating methods, primarily based on radiometric analysis of zircon crystals preserved within the volcanic and associated sedimentary rock, indicate that this activity occurred in pulses over a span estimated at approximately 1 million years, with the most intense phase of activity concentrated within a window of roughly 300,000 to 500,000 years. occurring in close temporal proximity to the broader environmental changes affecting both terrestrial and marine ecosystems during this interval. The total volume of lava and associated volcanic material produced during this period is estimated, based on the thickness and areal extent of preserved deposits, at approximately 3 to 4 million cubic kilometers. To place this figure in perspective, this volume substantially exceeds that of any volcanic event documented within the more recent geological record, including events from the past several million years that are themselves considered exceptionally large by the standards of recent Earth history. In some locations, particularly within the central portion of the affected region, individual lava flow sequences reach cumulative thicknesses exceeding 3,000 meters, representing the accumulation of numerous individual flows, each of which may have extended laterally for distances of tens to, in some documented cases, several hundred kilometers from its source. The physical process by which these lava flows developed and spread is informed by both the physical properties of the erupted material and by comparison with smaller scale, though still substantial, basaltic eruptions documented in more recent geological history. Basaltic lava of the composition, indicated by preserved samples from this interval, typically erupts at temperatures between 1,100 and 1,200 degrees Celsius, with relatively low viscosity compared to other lava compositions, allowing it to flow over land surfaces at rates that, for well-documented modern analogues, have reached several kilometers per day under conditions of high effusion rate, meaning a high volume of lava erupted per unit of time. Given the total estimated volume of material produced over the most intense phase of this activity, average effusion rates during peak periods are estimated to have been substantially higher than those observed in any directly comparable modern eruption, potentially by one or more orders of magnitude. At such rates, individual lava flows could plausibly have advanced across landscapes at speeds sufficient to overtake any terrestrial animal attempting to flee on foot, though the geographic extent of any single flow event, while substantial in absolute terms, represented only a portion of the total area affected by the broader eruptive sequence over its full duration. Beyond the direct physical effects of lava emplacement, which would have resulted in the immediate and complete destruction of any pre-existing terrestrial ecosystem within the area covered by individual flows, the eruptive process released substantial quantities of volcanic gases into the atmosphere. Basaltic eruptions of this type typically release significant volumes of carbon dioxide, sulfur dioxide, and, depending on the specific geological setting, other gases, including chlorine and fluorine compounds, with the relative proportions depending on both the composition of the erupting magma and the composition of any crustal rock through which the magma passed on its way to the surface. In the specific case of the Siberian traps, geological evidence indicates that the erupting magma, in at least some locations, passed through and interacted with extensive deposits of sedimentary rock containing significant quantities of organic carbon, evaporite minerals, and coal. This interaction is significant because the heating of such material by intruding magma, a process that can occur both at depth, before material reaches the surface, and at the surface itself, where lava flows over or intrudes into these deposits, can result in the release of additional gases beyond those directly contained within the magma itself, including substantial additional volumes of carbon dioxide and methane derived from the thermal breakdown of organic-rich sedimentary material. Evidence for this process comes from the identification of numerous structures within the Siberian Traps region, interpreted as the remnants of explosive vents formed by the rapid release of gas, generated through exactly this kind of conning. Magma-sediment interaction structures that, in some cases, contain fragments of the sedimentary rock through which the gas-generating interaction occurred. providing direct physical evidence of the materials involved. The total additional volume of carbon dioxide and methane potentially released through this mechanism, while difficult to constrain precisely, is estimated by some current models to be comparable to, or in some scenarios, to exceed, the volume of carbon dioxide released directly from the magma through normal volcanic outgassing processes. The cumulative effect of this volcanic activity, considered purely in terms of its direct physical footprint, was the transformation of a substantial portion of what had been terrestrial landscape, including, based on the geographic context, areas that would have included some of the higher latitude forested regions discussed in relation to the broader climatic changes occurring during this period into a landscape dominated by exposed volcanic rock, extending in places to the horizon in multiple directions, with active lava flows, vents releasing gas and ash, and underlying terrain reshaped by the cumulative emplacement of material reaching thicknesses in the most affected areas of several kilometers when measured from the original pre-eruption land surface to the top of the final accumulated volcanic sequence. The volcanic activity occurring across the Siberian region during this interval released gases into the atmosphere at rates and in quantities that exceeded the capacity of existing planetary systems to process or absorb them at equivalent speed. Carbon dioxide, the primary gas of concern in terms of its effect on global climate, accumulates in the atmosphere when its rate of release exceeds the combined rate at which it can be removed through processes including absorption by ocean water, uptake by photosynthetic organisms, and incorporation into newly forming sedimentary rock through chemical weathering of exposed continental surfaces. Under typical conditions prior to this interval, these removal processes operated at rates sufficient to maintain atmospheric carbon dioxide concentrations within a relatively stable range over periods of millions of years, despite ongoing background levels of volcanic outgassing from sources distributed across the planet. The scale of carbon dioxide release associated with the Siberian Traps eruptions, however, is estimated by current models to have substantially exceeded these background rates, potentially by a factor of 10 or more during the most intense phases of activity, over a period short enough, several 100,000 years, that the slower acting removal processes, particularly chemical weathering, could not respond at a comparable rate. The result was a measurable and relatively rapid increase in atmospheric carbon dioxide concentration. Estimates derived from multiple independent proxy methods, including the carbon isotope composition of preserved organic material and the boron isotope composition of preserved marine carbonate, indicate that atmospheric carbon dioxide concentrations increased from levels already elevated relative to earlier geological baselines, estimated at 1,000 to 2,000 parts per million prior to this interval, to concentrations potentially exceeding 3,000 to 4,000 parts per million by the conclusion of the most intense eruptive phase, representing a near doubling or greater over a span estimated at less than 100,000 years in some reconstructions. The direct physical consequence of this increase in atmospheric carbon dioxide concentration was an enhancement of the greenhouse effect, the process by which certain atmospheric gases absorb and re-emit infrared radiation, retaining heat within the atmosphere that would otherwise be radiated back into space. The magnitude of warming associated with a given increase in carbon dioxide concentration is generally expressed in terms of climate sensitivity, a value representing the temperature increase expected for each doubling of atmospheric carbon dioxide concentration. Estimates of climate sensitivity applicable to this interval derived from the relationship between estimated carbon dioxide concentrations and independently estimated temperature changes preserved in isotopic proxies suggest values broadly consistent with those derived for other intervals in Earth's history. generally in the range of 3 to 5 degrees Celsius of warming per doubling of carbon dioxide concentration. Applied to the carbon dioxide increase estimated for this interval, this relationship is consistent with the global average temperature increases of 5 to 8 degrees Celsius, indicated by independent temperature proxies for this period. Proxies that include the oxygen isotope composition of preserved marine carbonate, which varies in a predictable manner with the temperature of the water in which the carbonate formed, after accounting for other factors that can also influence this isotopic ratio, including changes in global ice volume. Though ice volume during this interval is understood to have been minimal, given the already warm baseline conditions established in earlier portions of the Permian. Beyond carbon dioxide, the volcanic activity associated with the Siberian traps also released substantial quantities of sulfur dioxide, a gas that, upon release into the atmosphere, undergoes chemical reactions leading to the formation of sulfate aerosols, small particles that can have effects on climate distinct from, and in some respects opposite to, those associated with carbon dioxide. Sulfate aerosols reflect incoming solar radiation, producing a cooling effect at the surface. But this effect is generally short-lived, with aerosols typically removed from the atmosphere through precipitation within periods of weeks to a few years, depending on the altitude reached by the aerosols and the specific atmospheric conditions present. In addition to their climatic effects, sulfur dioxide and the sulfate aerosols derived from it contribute directly to the acidification of precipitation through chemical reactions in which sulfur dioxide combines with water vapor to form sulfuric acid, which is then incorporated into raindrops. The sustained release of sulfur dioxide over the duration of the most intense volcanic activity is consistent with sustained periods of acidified precipitation across regions affected by atmospheric transport of these gases, with the geographic extent of such effects depending on prevailing wind patterns and atmospheric circulation, but potentially extending across large portions of Pangaea, given the substantial total quantity of sulfur dioxide estimated to have been released. Acidified precipitation has direct effects on terrestrial vegetation through damage to leaf surfaces that can impair photosynthetic function, and through alteration of soil chemistry, particularly through the leaching of essential plant nutrients, including calcium and magnesium, from soil, a process that occurs when acidic water passing through soil dissolves and removes these nutrients at rates exceeding their natural replenishment through mineral weathering. For vegetation already under stress from the temperature and precipitation changes described in relation to forest dieback occurring during this broader interval, the additional stress imposed by acidified precipitation and associated soil nutrient depletion represents an additional factor contributing to the overall decline in vegetation, health, and extent. The combination of substantially elevated greenhouse gas concentrations, the resulting global temperature increase, and the associated changes in precipitation chemistry collectively describe an atmospheric system that, by this point in the interval, differed substantially from the system that had existed only a few 100,000 years earlier, a difference not merely in degree but, in several respects, in the fundamental balance of processes governing the composition and behavior of the atmosphere, where earlier conditions had reflected a long-term equilibrium between gas release and gas removal processes operating over millions of years. The conditions developing during this interval reflected a system in which release rates had, for a geologically brief period, substantially outpaced the removal processes capable of restoring that equilibrium, a circumstance with consequences that extended across every major component of the planet's surface systems, from the composition of the atmosphere itself, to the chemistry of ocean water, to the physiological tolerances of organisms across both terrestrial and marine environments. By this point in the interval, the individual processes described in relation to terrestrial drying, forest decline, oceanic oxygen depletion, and atmospheric transformation had each progressed to the point where their combined effects began to manifest as simultaneous, large-scale ecosystem failure across both terrestrial and marine environments. Current stratigraphic dating, based primarily on radiometric ages obtained from volcanic ash layers preserved within marine sedimentary sequences that also record biological extinction patterns, places the period of most severe biodiversity loss within a window estimated at less than 100,000 years, and potentially as short as 20,000 to 60,000 years in some high-resolution sequences, a duration that, while substantial relative to individual organism lifespans, represents a geologically abrupt transition when compared to the tens of millions of years over which the preceding ecosystems had developed. The magnitude of biodiversity loss documented for this interval exceeds that of any other extinction event identified within the fossil record, including events affecting later periods of Earth's history that are more widely recognized in general discussion of extinction events. Based on the analysis of marine fossil occurrence data across thousands of documented genera, current estimates indicate that approximately 81 to 96% of marine species present prior to this interval do not appear in fossil assemblages from immediately afterward, with estimates for the percentage of genera, a broader taxonomic category encompassing multiple related species lost during this interval, generally falling in the range of 50 to 60%. For terrestrial ecosystems, quantifying extinction severity presents additional methodological challenges due to generally lower preservation rates for terrestrial organisms compared to marine environments, where continuous sediment accumulation on ocean floors provides more complete fossil records. Nonetheless, current estimates based on available terrestrial fossil data suggest that approximately 70% of terrestrial vertebrate genera present prior to this interval are absent from fossil assemblages representing the period immediately following, a figure broadly consistent in magnitude, though derived from a more limited dataset, with the marine estimates described above. The simultaneity of these losses across both marine and terrestrial environments is significant in terms of identifying potential causal mechanisms, since it indicates that whatever processes drove this extinction event must have been capable of affecting fundamentally different types of ecosystems. Ecosystems that, under normal circumstances, are subject to substantially different environmental pressures and operate according to different ecological dynamics within a comparable time frame. The mechanisms described in preceding portions of this account, particularly the global temperature increase driven by elevated atmospheric carbon dioxide and the associated expansion of low oxygen conditions in ocean water, represent processes capable of exerting this kind of broad, cross-ecosystem effect, since both temperature and, in the case of marine environments, oxygen availability function as fundamental constraints on the physiological functioning of essentially all complex animal life, regardless of the specific ecosystem in which that life occurs. Within marine environments specifically, the pattern of extinction shows some variation according to the physiological characteristics of different organism groups, consistent with oxygen availability functioning as a primary driver of mortality. Organisms with limited capacity for active movement, including many reef-building groups and various sessile meaning permanently attached to a substrate invertebrates, show particularly severe losses, consistent with their inability to relocate in response to expanding low oxygen conditions. Organisms with greater mobility, including many fish groups and certain mobile arthropods, show comparatively, though still substantially, lower extinction rates, consistent with at least some capacity to move toward more favorable conditions, where such conditions remained available within reachable distances. Within terrestrial environments, the pattern of extinction during this interval shows a less straightforward relationship to body size and ecological role than might be predicted based on the patterns of competitive and resource-based pressure described in relation to the preceding several 100,000 years. While larger predators and herbivores do show substantial losses, consistent with the trends toward decline already underway prior to this interval, certain smaller organisms also show significant losses, including groups that, based on the analysis presented in relation to earlier portions of this broader transition, had appeared comparatively resilient to the more gradual pressures of habitat fragmentation and resource decline that characterized the preceding interval. This pattern is consistent with the interpretation that the most severe portion of this extinction event involved environmental changes of a magnitude sufficient to exceed the physiological tolerances of organisms broadly, rather than changes that primarily acted through more indirect mechanisms such as competitive exclusion or gradual habitat loss mechanisms that, while clearly operative during the preceding several 100,000 years based on the evidence presented in earlier portions of this account, would be expected to produce extinction patterns more strongly correlated with specific ecological characteristics, such as body size, dietary specialization, or habitat requirements, rather than the broader pattern observed for this most intensive interval. The geographic distribution of fossil evidence from immediately following this interval shows a marked reduction not only in the diversity of organisms present, but in the overall abundance of fossil material of any kind within many sedimentary sequences, a pattern sometimes described in the relevant literature as a coal gap, referring specifically to the near-total absence of coal deposits, which form from accumulated plant material under specific conditions, within sedimentary sequences spanning a period estimated at several million years following this interval, despite coal deposits being relatively common in sequences both preceding this interval and resuming, in modified form, within Mesozoic sequences. This absence is consistent with the near-total loss of the specific types of forest ecosystems, particularly the extensive conifer and cordatalian forests, described in relation to earlier portions of this account that had provided the plant material from which earlier coal deposits had formed. Considered collectively, the evidence available for this interval describes a period during which the gradual, multi-factor decline affecting both terrestrial and marine ecosystems over the preceding several 100,000 years transitioned into a more rapid and more comprehensive collapse, affecting essentially every major ecosystem type and a substantial majority of the species occupying those ecosystems within a time frame that, by the standards of the geological record, occurred close to instantaneously, establishing conditions for the subsequent intervals that would be defined, in fundamental ways, by the absence of organisms and ecological relationships that had, until this point, been continuous features of life on Earth for tens of millions of years. The extinction patterns described for the preceding interval did not affect all components of any given ecosystem simultaneously and to an equal degree, despite occurring within a geologically compressed time frame. Instead, evidence from sequences that preserve sufficient temporal resolution to distinguish events occurring within this brief interval indicates that losses propagated through ecosystems according to identifiable sequences, beginning with specific groups of organisms and subsequently affecting other groups whose survival depended, directly or indirectly, on the organisms lost in the initial phase of decline. Within marine ecosystems, primary productivity, the rate at which photosynthetic organisms, primarily various groups of marine algae and cyanobacteria, convert solar energy into organic material that forms the energetic foundation for essentially all other marine life appears. Based on the analysis of preserved organic carbon isotope ratios in marine sediments from this interval, to have undergone a substantial and relatively abrupt decline. Carbon isotope ratios in marine sediments shift in predictable ways depending on the relative contribution of different types of photosynthetic organisms to overall productivity, and the shifts documented for sediments deposited during this interval are consistent with a substantial reduction in the contribution from larger, more complex photosynthetic organisms, with a corresponding relative increase in the contribution from smaller, more simple organisms, including various cyanobacteria groups that are generally associated with lower overall productivity and simpler food web structures. This shift in the base of the marine food web carries direct consequences for organisms occupying higher positions within that food web, since the total amount of energy available to support animal life within an ecosystem is fundamentally constrained by the productivity of the photosynthetic organisms at its base, with each successive level of the food web from primary consumers that feed directly on photosynthetic organisms to predators that feed on those primary consumers, and so on, generally able to support only a fraction, often estimated at around 10%, of the energy available at the level below it. A substantial reduction in base-level productivity, therefore, implies a correspondingly larger, proportionally amplified reduction in the energy available to support organisms at higher food web levels. Filter-feeding invertebrates, including various bivalve and brachiopod groups that obtained nutrition by filtering small particles, including photosynthetic organisms, directly from water, represent organisms occupying a position close to the base of the marine food web, and their decline during this interval, documented through the fossil occurrence data described in the preceding portion of this account, is consistent with direct effects of reduced primary productivity, in addition to the direct physiological effects of reduced oxygen availability described previously, with these two factors likely acting in combination rather than independently. For predatory organisms occupying higher positions within marine food webs, including various cephalopod groups and early marine reptiles, the decline of these lower food web components represents an indirect effect, operating through the reduction of their food supply, rather than through direct physiological intolerance of prevailing environmental conditions, though direct physiological effects would also have applied to these organisms to varying degrees depending on their specific tolerances for the temperature and oxygen conditions described previously. Fossil evidence for these higher-level predators from the interval immediately following the most severe extinction losses shows substantial reductions in both diversity and, where accessible, population density, consistent with the combined effects of direct environmental intolerance and indirect food supply reduction operating together. Within terrestrial ecosystems, an analogous pattern of cascading effects is evident, though operating through somewhat different specific mechanisms given the fundamental differences between terrestrial and marine food web structures. The decline of forest ecosystems, described in relation to earlier portions of this broader transition, had already substantially reduced the availability of plant material that had previously supported herbivorous animal populations, and the most intensive phase of extinction appears to have affected remaining herbivore populations severely, based on the fossil occurrence data described previously, indicating substantial losses among terrestrial vertebrate groups generally. The loss of herbivorous animals carries direct consequences for predatory animals that depended on those herbivores as a food source, in a manner directly analogous to the effects described for marine predators in relation to the loss of their invertebrate prey base. The Gorgonopsians and other large predatory synapsids, described in relation to earlier portions of this account, having already experienced population pressures associated with declining prey availability during the preceding several 100,000 years, appear, based on fossil occurrence data, to disappear from the fossil record entirely by the conclusion of this most intensive extinction interval, representing the complete loss of a group that had occupied dominant predatory positions within terrestrial ecosystems for tens of millions of years prior to this point. This pattern, in which the loss of organisms occupying lower positions within food web structures produces subsequent, often more severe. Effects on organisms occupying higher positions is sometimes described in ecological terms as a trophic cascade, referring to effects that propagate through multiple levels of a food web from an initial disturbance at one level. The specific sequence and timing of losses documented for this interval, to the extent that current stratigraphic resolution permits such sequences to be distinguished, is broadly consistent with this kind of cascading pattern, with primary producers and primary consumers showing evidence of decline slightly preceding, in terms of stratigraphic position, the more complete losses documented for predatory organisms occupying higher food web positions. It should be noted that the temporal resolution available for distinguishing these sequences remains limited, given the overall brevity of the interval in question relative to the resolution typically achievable through standard stratigraphic and radiometric dating methods, and current interpretations should accordingly be understood as representing the current state of evidence rather than definitively established sequences. Nonetheless, the overall pattern of an ecosystem in which the organisms occupying foundational positions within food web structures experienced decline that subsequently propagated, with apparent amplification, to organisms occupying higher positions is consistent with the broader principle that complex ecosystems depend on the continued functioning of their foundational components, and that disruption to those foundational components carries consequences that extend, often disproportionately, to every other component of the system that depends, directly or indirectly, upon them. Despite the magnitude of biodiversity loss documented for the preceding interval, the fossil record from the period immediately following indicates that complete biological extinction did not occur, and that certain organisms, and, in some cases, entire ecological communities persisted through this interval in locations that appear to have provided some degree of protection from the most severe environmental conditions affecting the broader planet. The identification and characterization of these locations, sometimes referred to in the relevant literature as refugia, a term denoting areas in which populations of organisms persist despite the disappearance of those organisms from the broader region they had previously occupied, represents an area of ongoing research, with current evidence indicating several distinct types of environments that appear to have functioned in this capacity. Among terrestrial vertebrates, one of the most thoroughly documented examples of persistence through this interval involves a small reptile genus known as Lystrosaurus, a dicynodont belonging to the same broader group of herbivorous synapsids discussed in relation to earlier portions of this account, though Lystrosaurus itself represents a smaller-bodied form, with adult body length typically in the range of 60 centimeters to just over 1 meter, considerably smaller than the larger dicynodont species that had occupied dominant herbivore positions prior to this interval. Fossil evidence indicates that Lystrosaurus, while present prior to this interval, was not among the more abundant or ecologically dominant herbivore groups of the preceding several million years. Following this interval, however, Lystrosaurus appears in fossil assemblages from multiple, widely separated geographic regions, including localities in present-day South Africa, Russia, India, China, and Antarctica, in some cases representing the substantial majority of identifiable vertebrate fossil material within assemblages from the immediately following interval, with some sampled localities showing Lystrosaurus comprising over 90% of identified individual specimens, a proportion dramatically higher than its representation in assemblages from prior to this interval. Several physiological and ecological characteristics have been proposed as potentially contributing to this pattern of persistence and subsequent relative abundance, based on comparative analysis with both contemporary organisms that did not persist and with modern organisms exhibiting analogous characteristics. Lystrosaurus skeletal anatomy, particularly features of the limb bones and rib cage, has been interpreted by some researchers as consistent with burrowing behavior, which, if accurate, would have provided a degree of protection from surface temperature extremes through access to the more thermally stable conditions present at modest depths below the surface conditions that, based on the analysis presented in relation to earlier portions of this account regarding subsurface temperature changes, would still have been affected by overall warming trends, but to a lesser degree and with greater stability than conditions at the surface itself. Additionally, dietary flexibility, the capacity to obtain adequate nutrition from a relatively broad range of plant material, rather than depending on specific plant species or plant parts, has been proposed as a contributing factor based on the relatively generalized dental morphology preserved in Lystrosaurus specimens, which lacks the more specialized features associated with dietary specialization observed in some other dicynodont groups that do not persist beyond this interval. Under conditions in which the availability of any specific plant resource had become unpredictable due to the broader patterns of vegetation decline described in relation to earlier portions of this account, an organism capable of utilizing whatever plant material remained locally available, regardless of specific type, would possess a measurable advantage over organisms requiring more specific dietary resources. Beyond Lystrosaurus, fossil evidence indicates the persistence of several other organism groups through this interval, generally characterized by relatively small body size and, where accessible, relatively broad ecological tolerances. Among predatory animals, certain smaller therocephalian species, generally under 1 meter in body length, appear in fossil assemblages from immediately following this interval, though typically in reduced diversity compared to assemblages from prior to the interval, consistent with the broader pattern of biodiversity reduction described previously, while still representing genuine persistence of the broader group across this interval. Within marine environments, persistence appears to have been similarly concentrated among organisms possessing specific characteristics, conferring tolerance to the low oxygen and elevated temperature conditions described in relation to earlier portions of this account. Certain bivalve groups, generally characterized by relatively small body size and the capacity to tolerate periods of low oxygen availability through metabolic adjustments that, in modern analogous organisms, can include substantial reductions in overall metabolic rate during periods of environmental stress, appear in fossil assemblages from immediately following this interval at locations where most other invertebrate groups are absent or represented only by isolated individual specimens. Certain fish groups also appear to persist through this interval, with fossil evidence indicating relatively broad geographic distribution for at least some persisting groups, consistent with the greater mobility of fish relative to many invertebrate groups, as discussed in relation to the differential extinction patterns described previously. The specific physiological characteristics enabling this persistence among fish groups remain an area of ongoing investigation, though general tolerance for variable oxygen conditions, a characteristic present to varying degrees among many modern fish groups, particularly those inhabiting environments such as shallow coastal waters or freshwater systems that naturally experience greater variability in oxygen availability than open ocean environments, represents one potential contributing factor consistent with the broader pattern of oxygen-related stress described as a primary driver of extinction during the preceding interval. The geographic distribution of locations yielding fossil evidence of persistence through this interval shows some pattern of concentration in higher latitude regions, including the Antarctic locality mentioned previously in relation to Lystrosaurus, consistent with the interpretation that higher latitude environments, while still affected by the overall global warming trend described in relation to earlier portions of this account, may have experienced somewhat less extreme absolute temperatures than lower latitude regions during this interval, potentially providing conditions falling within the physiological tolerance ranges of a somewhat broader range of organisms than was the case in more severely affected lower latitude regions. The organisms that persisted through this interval, while representing a small fraction of the diversity present prior to it, would subsequently constitute the entire biological foundation from which the ecosystems of the following interval would develop. In the period immediately following the most intensive phase of biodiversity loss, the fossil record across multiple continents and ocean basins indicates an interval characterized not primarily by the presence of new or different organisms, but by a pronounced reduction in the overall complexity and density of biological communities relative to conditions both before this broader transition and, notably, relative to conditions that would develop in subsequent intervals. Current stratigraphic evidence indicates that this low diversity interval persisted for a duration estimated at approximately 4 to 5 million years, representing a substantially longer period than the extinction interval itself, and raising questions, addressed through ongoing research, regarding the specific factors that constrained biological recovery during this span. Within terrestrial environments, fossil assemblages from this interval are characterized by markedly reduced taxonomic diversity compared to assemblages from prior to the extinction interval, with many sampled localities yielding evidence of only a small number of distinct vertebrate species, often dominated by the Lystrosaurus populations described in relation to the preceding portion of this account, alongside a limited number of additional reptile and amphibian groups. The overall structure of terrestrial ecosystems during this interval appears, based on this evidence, to have been considerably simplified compared to the multi-tiered predator-prey systems that had characterized terrestrial ecosystems prior to the extinction interval, with fewer distinct ecological niches occupied and reduced evidence of the kind of specialized predator-prey relationships that had been documented for earlier intervals. Vegetation during this interval shows a similarly reduced diversity, with fossil evidence indicating that the extensive forest ecosystems described in relation to earlier portions of this account did not promptly re-establish following the extinction interval, despite environmental conditions during at least portions of this low diversity interval appearing, based on independent climate proxies, to have moderated somewhat from the most extreme conditions documented for the extinction interval itself. Instead, vegetation during this interval appears to have been dominated by smaller, often fast-growing plant types, including various fern groups and other plants generally associated, in modern ecological contexts, with disturbed or unstable environments rather than with the more stable conditions typically required for the establishment of mature forest ecosystems. The persistence of reduced vegetation diversity over a span of millions of years, despite apparent moderation of some climatic extremes, has been interpreted by some researchers as potentially reflecting ongoing instability in climatic conditions during this interval, with evidence from some sequences indicating substantial fluctuations in temperature and precipitation patterns occurring repeatedly over relatively short timeframes, potentially tens of thousands of years per fluctuation throughout this broader low-diversity interval rather than a single stable climatic state. Under such conditions, the establishment of mature forest ecosystems, which, as discussed in relation to earlier portions of this account, depend on relatively stable conditions sustained over periods of decades to centuries for individual trees to reach maturity, would face ongoing obstacles even in the absence of the more extreme conditions documented for the extinction interval itself. Within marine environments, this low diversity interval is similarly documented through reduced taxonomic diversity in fossil assemblages, with many sampled sequences from this interval yielding evidence of only a small number of distinct invertebrate groups often dominated by the small bivalve groups described in relation to the preceding portion of this account as having persisted through the extinction interval. Reef ecosystems, which, as discussed in relation to earlier portions of this account, had been substantially affected by the conditions developing prior to and during the extinction interval, do not show evidence of re-establishment during this low diversity interval, with sedimentary sequences from this span generally lacking the kind of large, structurally complex biogenic accumulations that had characterized reef environments prior to this broader transition. Geochemical evidence from marine sediments deposited during at least the earlier portion of this low diversity interval continues to show indicators consistent with low dissolved oxygen conditions in at least some ocean regions, based on the same types of elemental enrichment patterns described in relation to earlier portions of this account, suggesting that the oceanic oxygen depletion documented for the period leading up to and during the extinction interval did not resolve promptly, but instead persisted, at least in some regions, for a substantial portion of this subsequent low diversity interval, potentially representing one factor contributing to the limited marine biological recovery documented for at least the earlier portion of this span. The combination of evidence from terrestrial and marine environments during this interval describes a planet in which, while biological activity continued, organisms were present, reproducing, and in some cases, persisting across multiple generations. Within the locations they occupied, the overall complexity of biological systems remained substantially reduced compared to conditions both before the broader extinction, transition, and compared to conditions that would eventually develop in subsequent intervals. Ecosystems during this span appear to have been characterized by relatively simple structures, dominated by a small number of generalist organisms occupying broad ecological roles, rather than the more specialized, multi-tiered structures involving larger numbers of species, occupying narrower ecological niches that had characterized earlier intervals and would characterize later ones. This combination of factors a planet still experiencing, in at least some regions, residual effects of the oceanic and atmospheric changes associated with the extinction interval, combined with apparent ongoing climatic instability affecting terrestrial environments, is consistent with the extended duration of this low diversity interval, representing a period during which the basic preconditions for the kind of sustained ecological stability required for the development of more complex, diverse biological communities had not yet been fully re-established. Despite the passage of a span of time that, in absolute terms, exceeds the entire duration of many subsequent biological transitions documented within the fossil record of later geological periods. As the conditions described in relation to the preceding low diversity interval gradually shifted based on independent climate proxies, indicating a progressive reduction in the frequency and magnitude of the short-term climatic fluctuations that had characterized the earlier portion of this broader span. Fossil evidence from subsequent stratigraphic intervals indicates the beginning of a measurable increase in the taxonomic diversity of both terrestrial and marine organisms, representing the initial stages of a recovery process that would continue, with varying rates of progress, over a span of several million years. Among terrestrial vertebrates, this interval is marked by the appearance, in fossil assemblages, of several reptile groups that are absent or only rarely represented in assemblages from the immediately preceding low diversity interval. Among these, a group known as archosaurs, a lineage that, based on skeletal characteristics including features of the skull and limb structure, is distinguished from other reptile groups present during this interval, and which would, over subsequent tens of millions of years, give rise to the lineages that include both crocodilians and, separately, the dinosaur and bird lineages appears in fossil assemblages from this interval in forms that, while generally small in body size, typically under 1 meter in total length, represent a measurable expansion in the diversity of reptile body plans present within terrestrial ecosystems compared to the preceding interval. The expansion of archosaur diversity during this interval appears, based on the range of skeletal characteristics preserved across different specimens, to encompass a range of different ecological roles, including forms with skeletal proportions consistent with primarily quadrupedal locomotion movement on 4 limbs, as well as forms with proportionally longer hind limbs relative to forelimbs, a characteristic that, in some modern reptile groups, is associated with at least partial bipedal locomotion, meaning movement primarily or exclusively on the hind limbs, particularly during rapid movement. This range of locomotor adaptations is consistent with these early archosaur groups occupying a range of different ecological niches, in contrast to the more ecologically restricted communities documented for the immediately preceding low diversity interval. Alongside the expansion of archosaur diversity, fossil evidence from this interval also indicates an expansion in the diversity of other reptile groups, including various lineages that, while not directly ancestral to later dominant groups, represent an overall increase in the range of body sizes, dental morphologies, and inferred dietary specializations present within terrestrial vertebrate communities compared to the preceding interval. This pattern of expanding diversity across multiple, taxonomically distinct reptile lineages simultaneously is consistent with the interpretation that the constraints limiting diversification during the preceding low diversity interval, whether related to ongoing climatic instability, residual effects of the broader extinction event, or some combination of factors had, by this point, relaxed sufficiently to permit multiple lineages to begin occupying a wider range of ecological niches than had been available during the immediately preceding interval. The herbivorous component of terrestrial vertebrate communities during this interval also shows evidence of diversification, with fossil assemblages indicating the presence of multiple dicynodont species in addition to Lystrosaurus, including forms with skeletal proportions, suggesting somewhat larger body sizes than Lystrosaurus itself, in some cases approaching or exceeding 2 meters in total length, though still generally smaller than the largest dicynodont species documented from intervals prior to the extinction event described previously. This pattern of expanding herbivore diversity and, in some cases, increasing body size is consistent with a corresponding expansion in the availability of plant resources, which would in turn be consistent with the beginning of vegetation recovery in at least some terrestrial environments during this interval, though current evidence suggests this vegetation recovery remained incomplete relative to pre-extinction conditions, with the extensive conifer-dominated forest ecosystems described in relation to earlier portions of this account not yet re-established in their previous form or extent. The expansion of herbivore diversity and body size during this interval would be expected, based on general ecological principles regarding the relationship between herbivore abundance and predator populations, to be accompanied by a corresponding expansion in predator diversity, as an increased availability of herbivore prey would provide the resource base necessary to support a more diverse predator community. Fossil evidence from this interval is consistent with this expectation, with assemblages showing the presence of multiple predatory reptile groups, including forms occupying a range of body sizes from relatively small, generally under 1 meter, to moderately large, with some specimens indicating body lengths approaching 3 meters, though notably, none of these predatory groups appear closely related to the Gorgonopsians that had occupied dominant predatory positions prior to the extinction interval, that group having disappeared entirely as described in relation to earlier portions of this account. Within marine environments, this interval similarly shows evidence of expanding diversity, with fossil assemblages indicating the appearance of new invertebrate groups, including some forms with skeletal or shell characteristics distinct from those of the small bivalve groups that had dominated assemblages from the preceding low-diversity interval, as well as evidence of renewed activity by burrowing organisms within seafloor sediments, activity that, as discussed in relation to earlier portions of this account, had been substantially reduced or absent during the periods of low oxygen availability associated with both the extinction interval and at least the earlier portion of the subsequent low diversity interval, and whose renewed presence during this interval is consistent with at least partial recovery of dissolved oxygen conditions in the marine environments where this evidence has been documented. Considered collectively, the evidence from this interval describes a transition from the simplified, low-diversity ecological communities of the preceding interval toward communities characterized by a wider range of body sizes, ecological roles, and taxonomic groups, occurring across both terrestrial and marine environments, and involving, in several cases, the initial diversification of lineages, including the archosaur groups discussed at the outset of this account of this interval, that, while occupying relatively modest ecological positions at this stage, would over subsequent tens of millions of years undergo substantial further diversification and would come to occupy ecological positions of considerably greater prominence than those evident in the fossil assemblages currently available. For this particular interval, building on the expansion in taxonomic diversity documented for the preceding interval, fossil assemblages from subsequent stratigraphic intervals indicate a continuation and, in several respects, an acceleration of this diversification process, with evidence pointing toward the establishment of ecological structures that, while still differing in specific composition from those documented prior to the extinction interval discussed earlier, begin to exhibit a degree of complexity and stability broadly comparable to that of earlier, pre-extinction ecosystems, based on measures including the number of distinct trophic levels represented and the range of body sizes present within sampled communities. Within terrestrial environments, this interval is characterized by continued diversification among archosaur lineages, with fossil evidence indicating the appearance of forms showing increased body size relative to those documented for the immediately preceding interval, including some specimens with estimated body lengths exceeding 3 meters, alongside continued diversification in skeletal proportions consistent with a range of locomotor strategies. Among these forms, evidence indicates the presence of both herbivorous and carnivorous archosaur lineages, representing an expansion in the ecological roles occupied by this broader group compared to the more limited range of roles evident in fossil assemblages from the preceding interval. The herbivorous component of terrestrial vertebrate communities during this interval shows continued diversification beyond the dicynodont groups discussed in relation to the preceding interval, with fossil evidence indicating the presence of additional herbivorous reptile groups exhibiting dental and jaw structures consistent with the processing of increasingly varied plant material, including forms with dental morphology suggestive of the capacity to process more fibrous plant tissue than had been required by the dietary specializations of earlier herbivore groups. This expansion in dietary specialization among herbivores is consistent with, and likely reflects, continued recovery and diversification of terrestrial vegetation during this interval, with fossil plant assemblages from this span showing increased representation of gymnosperm groups, including early conifer relatives, alongside the fern-dominated assemblages that had characterized vegetation during the preceding low-diversity interval, indicating a transition toward vegetation communities incorporating a broader range of plant types than had been present during the immediately preceding span. Predator-prey relationships during this interval, as inferred from the co-occurrence of predator and prey body sizes and skeletal characteristics within sampled assemblages, show evidence of increasing specialization compared to the preceding interval, with some predatory archosaur lineages showing skeletal characteristics, including features of the skull and dentition, consistent with specialization toward particular prey size ranges or particular prey capture. Strategies. In contrast to the more generalized predatory morphology evident in fossil assemblages from the immediately preceding interval, this pattern of increasing specialization among predators is consistent with the broader pattern of increasing ecosystem complexity. Since specialization of this kind generally develops based on principles observed in modern ecosystems under conditions of relatively stable resource availability over periods sufficient for evolutionary adaptation to specific ecological niches to occur, conditions that, based on the evidence presented in relation to this interval, appear to represent an improvement in stability compared to the more variable conditions inferred for the preceding low-diversity interval. Within marine environments, this interval shows continued diversification among invertebrate groups, with fossil assemblages indicating increased representation of mollusk groups, including both bivalves and various gastropod forms, exhibiting a range of shell morphologies consistent with a range of feeding strategies, including both filter feeding forms, similar to those that had persisted through the preceding intervals, and forms with shell and, where preserved, soft tissue characteristics, consistent with active predation on other invertebrates, representing an expansion in the range of feeding strategies represented within marine invertebrate communities compared to the more limited range evident during the preceding low-diversity interval. Evidence from this interval also indicates the beginning of renewed reef-building activity in at least some marine environments. Though the organisms responsible for this renewed reef construction differ, based on the taxonomic characteristics of preserved skeletal material, from the organisms that had constructed reef systems prior to the extinction interval discussed earlier, with this interval's reef structures incorporating different combinations of calcifying organism groups than had been present in pre-extinction reef systems. While these renewed reef structures during this interval generally remain smaller in scale, both in terms of areal extent and in terms of accumulated thickness, than the pre-extinction reef systems described earlier in this account, their presence indicates that conditions, including water temperature, oxygen availability, and water chemistry, had, by this point, recovered sufficiently in at least some marine environments to support the kind of sustained biological calcification activity required for reef construction. Conditions that had not been met during the preceding low-diversity interval based on the absence of comparable structures in sediments from that span. The overall pattern of evidence from this interval, considered in combination with the evidence presented for the preceding interval, describes a progressive re-establishment of ecological complexity occurring across both terrestrial and marine environments. Proceeding through a sequence in which initial diversification among a limited number of lineages, as documented for the preceding interval, gave way to broader diversification, encompassing increased body size ranges, increased dietary and predatory specialization, and the renewed presence of ecological structures, including reef systems and increasingly complex terrestrial food webs that had been absent during the intervening low-diversity interval. This re-established ecological structure, while distinct in its specific taxonomic composition from the ecosystems present prior to the extinction interval, represents the foundational arrangement of organisms and ecological relationships from which the more extensively diversified ecosystems of subsequent geological intervals, including those incorporating the further diversification of archosaur lineages into the forms that would come to occupy dominant ecological positions in later periods, would continue to develop. Comparative analysis of the extinction interval described in earlier portions of this account, relative to other extinction events documented within the fossil record, including the event occurring approximately 186 million years later, associated with the disappearance of non-avian dinosaurs and numerous other groups, indicates several respects in which this earlier event differs substantially in both magnitude and underlying causation from these subsequent events, differences that carry direct implications for understanding the broader trajectory of life on Earth across the intervening and subsequent intervals. In terms of magnitude, the percentage estimates of species and genus-level loss documented for this interval, discussed in relation to earlier portions of this account, exceed the corresponding estimates for other extinction events documented within the fossil record by a substantial margin. The event associated with the disappearance of non-avian dinosaurs, by comparison, is estimated to have resulted in the loss of approximately 75% of species present at the time, a figure that, while substantial, falls below even the lower bound of the 81 to 96% range estimated for marine species loss during the interval discussed throughout this account. This difference in magnitude is consistent with the difference in recovery duration documented for the two events, with the low diversity interval following the event discussed in this account persisting for several million years, as described previously, compared to recovery timeframes generally estimated at under 1 million years for the more rapid aspects of recovery following the later event. Though full recovery of certain ecosystem types following the later event is itself estimated to have required several million years in some cases. In terms of underlying causation, current evidence, as presented throughout this account, indicates that the extinction interval discussed here resulted from a combination of factors operating over an extended timeframe, encompassing the gradual climatic and ecological changes described in relation to the several 100,000 years preceding the most intensive extinction interval, combined with the more rapid changes associated with the volcanic activity and associated atmospheric transformation described in relation to the Siberian traps. This combination of gradual, long-term environmental deterioration with a more acute, geologically rapid triggering event differs from the causation generally proposed for the event associated with the disappearance of non-avian dinosaurs, which current evidence associates primarily with the impact of an extraterrestrial body, an event occurring effectively instantaneously by geological standards, without the extended preceding period of gradual environmental change documented for the interval discussed throughout this account. This difference in causation carries implications for understanding the differing severity of the two events, since an extinction process operating through a combination of long-term ecological stress, which would have already reduced the resilience of affected populations prior to the most acute phase of the event, combined with an acute triggering event of substantial magnitude, would, based on general ecological principles regarding the relationship between pre-existing population stress and vulnerability to additional disturbance, be expected to produce more severe outcomes than an acute event of comparable or even greater immediate magnitude occurring without this kind of preceding period of cumulative stress, a pattern broadly consistent with the comparative and meta-severity estimates discussed above, though it should be noted that direct comparison of causal mechanisms across events separated by such substantial timeframes and documented through fossil records of differing completeness involves inherent uncertainties that current evidence cannot fully resolve. The long-term consequences of the extinction interval discussed throughout this account for the subsequent trajectory of life on Earth are evident in the specific composition of the ecosystems that developed during the recovery. Intervals described in the preceding two portions of this account. The disappearance of Gorgonopsians and the broader reduction in diversity among synapsid groups generally, combined with the diversification of archosaur lineages during the recovery intervals, represents a shift in the relative ecological prominence of these two broader reptile groups that, based on the fossil evidence from subsequent geological periods, persisted and, in several respects, intensified over the following tens of millions of years. with archosaur-derived lineages, including the dinosaur groups that would develop from the early forms discussed in relation to the recovery intervals, coming to occupy many of the large-bodied terrestrial predator and herbivore ecological roles that, prior to the extinction interval, had been occupied primarily by synapsid groups. This shift in ecological dominance between major reptile lineages represents one example of a broader principle evident in the fossil record: that extinction events of sufficient magnitude do not simply remove organisms from ecosystems and then permit the same organisms, or their close relatives, to subsequently re-expand into the ecological positions they had previously occupied. Instead, the removal of dominant groups during an extinction event creates ecological opportunities that may be occupied during subsequent recovery by different organisms than those that had occupied analogous positions prior to the event. Organisms whose own evolutionary history prior to the extinction event may have positioned them as relatively minor components of pre-extinction ecosystems, as was the case for the early archosaur lineages discussed in relation to the recovery intervals. The broader patterns evident across this account of ecosystems developing over tens of millions of years under relatively stable conditions, subsequently experiencing a combination of gradual environmental deterioration and acute triggering events leading to widespread ecological collapse, followed by an extended period of reduced diversity and ecological simplification, and eventually a recovery process resulting in ecosystems of renewed complexity but altered composition represent a sequence that, based on the comparative evidence available from other extinction events documented within the fossil record, appears to reflect general principles governing the response of biological systems to environmental change at this scale, rather than features specific to the particular interval discussed throughout this account. The specific magnitude, causation, and consequences of this interval, however, as documented through the evidence presented throughout this account, represent the most severe instance of this general pattern currently identified within the available fossil record, with effects on the subsequent composition of life on Earth that remain identifiable within the fossil record of intervals occurring tens of millions of years afterward.